Okay, so let us continue our permutation group exercises now with this one. Again, we are in the symmetry group of degree in Sn, where now we are considering two cycles, alpha and beta. Alpha is a 2 cycle and beta is a t cycle. We have to prove that then alpha beta alpha is also some t cycle. So let's see the solution. Let alpha is given to be a 2 cycle, so alpha will look like this. For some symbols A and B coming from the set of symbols, those n symbols on which the permutations from Sn are acting. Okay, so alpha is this and beta is the t cycle. Say beta is this. A t. Now some cases will arise and we have to handle the cases individually depending on how alpha intersects with beta, that is whether there is any symbol in common, if so how many are common. Depending on those things, some cases will arise, and the first case where alpha and beta actually do not have anything in common, that is when they are disjoint, is rather easy. So we write like this: when alpha and beta are disjoint, then we know that they commute alpha beta is equal to beta alpha, and hence alpha beta alpha will be equal to beta. In place of beta alpha we can write alpha beta, that is alpha square beta, but because alpha is a 2 cycle, alpha square equals the identity, so this is equal to beta, which is just again the same t cycle, but it's a t cycle, and that's what we want to show. So we don't even write anything else. It's understood that we have achieved what we want in this case. Next, the next case arises when, say, exactly one of the symbols in alpha is also there in beta and the other is not. So let A be equal to A1 and B be not equal to AI for all I between 1 and t. Now you may be wondering, why are we assuming that A is equal to A1? Is it not possible that A is, say, equal to A2 or some other AI? Of course that is possible, but keep in mind that you can write a given cycle in several different ways. You just have to make sure that the cyclic order is maintained. So if you want, I think I discussed about this before also, if you want you can start this cycle by writing A2 first and then follow that up with A3, and then you reach AT and then you write A1. That also represents the same cycle. So if this A turns out to be equal to some AI somewhere in the middle, you can choose to write beta in that way where the first symbol is AI. So without loss of generality, actually we are assuming that A is equal to A1. If you want, you can use that phrase also. Next, assume without loss of generality that A is equal to A1 and B is not equal to any AI. Okay, but I have chosen to not write it that way, but you understand what the situation is here. Okay, now we have to actually calculate alpha, beta, alpha. It's not as easy as this first case, but let's see what happens. Then alpha, beta, alpha is equal to, what shall we have? Let us write this also as A1, and B is of course B, and then we write beta. AT times the gain alpha. Now we are going to calculate this product, where again we recall that things start from this side. That is, you start from the rightmost end of such a product and then move leftward. So we start off with A1. A1 is sent to B by this permutation, this cycle, and then that B is nowhere to be seen here. So that means this middle one does not affect B, it maps B to itself, and then this leftmost one sends that B back to A1. That means ultimately A1 is mapped to A1 itself. In other words, this product actually does not affect A1. Okay. Next we look at A2. This one does not affect A2 because B is A1 of course is different from A2, and B is not equal to any of them. So in particular B is not equal to A2. So this one does not affect A2. This one sends A2 to A3, and that A3 then is again unaffected by this leftmost one. So that means A2 is sent to A3 by the entire product, and it goes on like this until what? Say you have reached a t minus 1, okay, and then a t minus 1 is unaffected by this. The middle one only affects a t minus 1, it sends a t minus 1 to a t, and then that a t again further is unaffected by this one. So that means a t minus 1 is sent to a t. Fine. Then we look at AT. AT is unaffected by this. AT is sent by this middle one to A1, and then that A1 this time around is affected by this leftmost one, and it sends that A1 to B. So that means ultimately AT is being sent to B. Okay. And then we look at B. B is first sent by this one to A1, and then A1 is sent to A2, and this one does not affect A2. So that means B is sent to A2. That means the beginning. So here things end, and we see that all the elements A2, A3, I mean all the symbols, these are being affected by this entire product. The only thing that is unaffected is A1. Okay. So now you can easily see that this is again a T cycle, because we have lost one symbol A1 and in its place we have gained one symbol B. So after all, it's a T cycle, which is a T cycle. Fine. Now we have only one more case left, that is that both A and B are present here, and one of them, say A of course we can again consider it to be A1, but B will be then something arbitrary here, something other than A1. That you cannot do anything by writing without loss of generality. You won't lose generality. But if you say take B equal to A2, you are actually considering only one special case, that is not general. So the next case we write like this: next let like before, like the second case, let A be equal to A1 and B this time is equal to say AJ for some J lying between 2 and T. We cannot take J equal to 1 because it has already been taken. Then this time also we are in for some calculation, alpha, beta, alpha. Let us first write what we have here. A1, AJ. I will need more space than before to write this one because we have something in the middle. No? Now something in the middle, I say in general, I am saying it may turn out that J is equal to T. That case is also included. So in general we write like this. Beta looks like this. A2 AJ minus 1. And you do understand why we are taking A equal to A1. If you want, you may choose to not write something like that. You may actually assume that A is equal to some AI and then B is equal to some AJ, but that would create unnecessary complexity, especially when there is a way of simplifying things without losing any generality. So we took advantage of that and we are considering A equal to A1. Okay, so we now continue. Then the next symbol is AJ, then AJ plus 1, and like that we get to 8. Because we have taken so much space, so why not write T minus 1 also times A1 AJ. Okay, now we calculate the product like before. So we start with A1. So this one first, A1 is sent to AJ. Here the situation is much more complicated. This one is sending A1 to AJ, then the middle one beta sends AJ to AJ plus 1, and then this one does not have AJ plus 1, so it will not affect AJ plus 1. So that means A1 is actually sent to AJ plus 1. Next, what about AJ plus 1? Naturally we would look at that next. AJ plus 1 is unaffected by this, and the middle one sends AJ plus 1 to this next one which we haven't written, AJ plus 2, and this one then does not affect AJ plus 2. So AJ plus 2. And it continues like this. Somewhere it has to stop. Say we look at AT minus 1. AT minus 1 you don't see here. You see, you have to understand that, okay, you may say that because J is not something fixed, it may happen that J is equal to T minus 1. That may happen, but the way we have written this middle one, the beta, that just simply tells us that AJ is here and AT minus 1 is here. So if J is actually equal to T minus 1, then that case will be taken care of here itself. The thing is that the way, let us just complete the calculation and you will understand once it's complete that the case where J is equal to T minus 1 is included in this itself. It may be somewhat confusing at this point to see that everything is actually being taken care of at once, but once we finish this you will see that things fall in place and it's okay. So let us just treat these things as separate symbols. So what we are now doing is we are going to look at a t minus 1, because if we continue like this, we would eventually get to a t minus 1, and now we are looking at a t minus 1. So assuming that t minus 1 is not equal to j, this thing does not affect a t minus 1. This thing sends a t minus 1 to a t, and then this thing does not affect that a t, assuming again that t is not equal to j. Okay, so we get to a t, but now we look at a t. Okay, so because we have already assumed that t is not equal to j, so this one does not affect a t. This one sends a t to what? A t back to a1, but then that a1 actually is sent to aj by this one. So that means after at we will have aj. Again I am saying, you see, in this calculation it seems like we are heavily using the fact that j is not equal to t minus 1 and at the same time j is not equal to t. But those cases also, I mean where those things are actually equal, they are included in this. So let's now continue. So this is aj, and then we look at the effect of this product on aj. So aj is sent to a1 by this rightmost one, then that a1 is sent to a2 by beta, and that a2 is unchanged by this. So that means aj is sent to a2. Next we look at a2. a2 is unchanged by this, a2 is sent to a3 by beta, and then that a3 is unchanged by this. So a similar thing is happening here in this part of the calculation, that we are saying, say, a2 is unchanged by this, a3 is unchanged by this. That requires us to actually assume that j is neither 2 nor 3. So those cases are also included here, although that may not be apparent at this point. So like this we will go until what happens? Say we hit aj minus 1. If we continue like this, we can expect that we will get aj minus 1. Okay. Now aj minus 1, here we don't have to assume anything. aj minus 1 actually is different from aj, because j minus 1 is not equal to j. There is no chance that they are equal. So this is unaffected by this, then this is then sent by this to aj, and that aj is sent to a1, back to a1. So that means here actually the thing ends and things cycle back to a1. Now having done the calculation, now you can look at those special cases. Say j equal to t. When j is equal to t, then you accordingly write beta, and you will see that still that same calculation is true, provided you write all the right things in their places. You write at here, and you will notice that there is no such thing as at plus 1, because the symbol only goes that far. In beta, the ai's go from 1 through t. So what is it that you will write here in that special case? Say you, for a moment, you think of this case, j equal to t. If you are really skeptical about this calculation working in general, you take this case j equal to t, then you will have a1 at, and then you start writing beta, and beta is just simply beta. But now the thing is that this is your aj, so aj minus 1 is there, aj plus 1 actually is not there. Okay, so this part is not available at all. I mean, this starting from right next to AJ, and before you hit 80, this intermediate part is not there. Okay, so you have to understand that. And then you of course write A1, A2. You calculate this freshly, separately, and then you see whether you get this thing itself. If J equals T, you will see that you are getting the thing. If you want, you can look at the other special cases, and by looking at some 2 or 3 cases, you will slowly get convinced that yes, the calculation works in general. Okay. So now the final cycle, we can see that the product has become a single cycle. We now have to calculate the length of this cycle. It will be a T cycle, we will see that, but let us first simply write which is a T cycle again. Okay, but is it a T cycle? How many symbols are there between, say, AJ plus 1 and AT, including AJ plus 1 and AT, of course? The number is T minus J plus 1 plus 1, because you have to include this also. Okay, and then how many symbols are there like that from A2 all the way through AJ minus 1? We have to add that J minus 1 minus 2 plus 1 to include A2. And what have we missed? We have missed this A1 and AJ. So that means plus 2. So what are we getting now? Minus J plus J, they cancel out. You see here minus 1 plus 1, they cancel out. Minus 1 plus 1, they cancel out, and minus 2 plus 2, they cancel out. So that means you are left with T. So this is actually a T cycle. And here the solution itself ends, because this was the only other case. So that means we are always getting a T cycle if we pre and post multiply a T cycle beta by a 2 cycle alpha, that is multiply on both sides. Alpha beta alpha is again of course not always equal to beta, that is just only one case, but in any case the length will not change, it will still be T, and it's going to be a T cycle, it won't be anything else. Fine, so this one is over. Now next we are now going to make matters a little bit more complicated. Use the previous exercise to prove that if alpha and beta belong to Sn, alpha and beta belong to the symmetric group Sn, and beta is the product of k cycles k cycles means k number of cycles, k number of permutations where each permutation is a cycle. k cycles of lengths. Lengths may vary, of course. Here the lengths are given n1, n2, etc. nk. Then alpha, beta, alpha inverse is the product of k cycles. Again, just like beta, alpha inverse is the product of k cycles of lengths n1, n2, etc. nk. In the text there is a hyphen between k and cycles, but I think it's a mistake because that means something else. Now, for example, here we have written t cycle. T cycle does not mean t number of cycles. Here, if you write like this, t hyphen cycle, that just means that this is the length of the cycle that you are mentioning. Okay. So now let's see what we can do for this one. So what is given to us is this. Use the so what do we have? Alpha and beta belong to Sn, and beta is the product of k cycles of lengths. So note that here there are differences, of course. Differences means it's not exactly like what we had in the previous exercise. In this case, beta is not necessarily just one cycle, but it's a product of k number of cycles, each one having its own length. If k is 1, then of course beta is like the one before. Alpha, on the other hand, is absolutely arbitrary. It's any element in Sn. There you had alpha equal to a 2 cycle. Now that is not the case. So let us first see how we can extend the result of the previous exercise in the simplest way. Note that it follows from the previous exercise that if alpha 1, alpha 2, etc., alpha m are 2 cycles, that is, each one of them is a 2 cycle, is a cycle of length 2, and gamma is a t cycle, then alpha 1, alpha 2, alpha m times gamma times alpha 1, alpha 2, alpha m is again a t cycle. How exactly are we getting this result? It's the generalization of the result of the previous exercise. Then it is very simple. What you do, let me just first clean the code. So what we are saying is that instead of having only 1 2 cycle, we have a number of 2 cycles. Now if you look at this, thing, then what do you see? Oh, we may be having a problem here, no? Why I am saying there will be a problem? No, there is no, actually not the way I have written here this product, that is a problem. But if I write inverse here, then there is no problem. This is, oh, we did not finish it, no? This is again a T cycle. Okay, but exactly how? I will not make the how part a part of this solution, but I will just simply show you. Now you know that in a group, when you take inverse of a product, then that equals the product of the individual inverses but taken in the opposite order. So that means alpha m inverse, there will be a previous one, alpha m minus 1 inverse. Like that we will have alpha 2 inverse, alpha 1 inverse. Now if you rearrange means actually you don't have to change order, but you regroup things in this manner. M minus 1, alpha m gamma, alpha m inverse. Then after that you of course have alpha m minus 1 inverse, and it will continue like that, alpha 2 inverse, alpha 1 inverse. And you also use that fact that because all these alphas are 2 cycles, so their inverses are the cycles themselves. This is also something we already know. So alpha m inverse is alpha m itself, just like that these other things are also themselves. Okay. Now on this, it is very easy and straightforward to see how we will use the result of the previous exercise. Because you see, now what do you have within this parenthesis? A 2 cycle, a T cycle, another 2 cycle, same 2 cycle. So by the previous exercise, this is again a T cycle. And then you repeat this process, because then you have a T cycle in the middle, on both sides of which you have alpha m minus 1, alpha m minus 1. So that then will become a T cycle, and this process will continue. Eventually, when you reach alpha 1 times the T cycle followed by another alpha 1, that also becomes the T cycle. Okay, so that's how we are saying that this is a T cycle. If you really want to prove this rigorously, of course, you should use induction. It will be extremely straightforward, but just use induction and it is straightforward. There is no twist to it. Okay, so that means this part there is no problem with this. And now comes the fact that because a product of 2 cycles behaves in this desired way, any permutation will behave in this way, because we already know that any permutation is actually a product of 2 cycles. So that is why this implies have we mentioned the previous, from the previous exercise. Okay, this implies we are directly writing, okay, not even mentioning that because any permutation is a product of 2 cycles, so the next thing that we are going to write here is true. This implies alpha gamma alpha inverse is a T cycle for any alpha belonging to Sn. So the confusion that I suddenly had here is simply because I was going to write exactly like what is written in the previous exercise, but we need the inverse here. The inverse actually it does not appear in the previous exercise because there we have only 2 cycle, but here we have any number of 2 cycles. Anyway, so this is something now we are going to use. But now our beta is not a single T cycle, it's in fact a product of K cycles, each one having a possibly a different length. So we now proceed like this. Now let beta be equal to gamma 1, gamma 2, gamma k, where gamma I is a cycle of length ni for all the variations of I, that is from 1 through k. Then then what is alpha, beta, alpha inverse? It is alpha, gamma 1, gamma 2, gamma k, alpha inverse, and that is equal to, you can in fact arrange things in this way in a very convenient manner like this. The same form can be now spread among all the gammas. Note that in this solution that we are currently writing, we actually are not writing absolutely all the details. We in fact are just simply mentioning many things which ideally speaking need proof. But you can clearly see that those statements, like for example this one, you need not show the proof here itself. That is because it's straightforward from our point of view. So this way, the more solutions you write, the more you will realize what to write and what to suppress. Alpha, gamma, k, what to suppress without compromising the solution. Okay, so now we are ready to use the thing that we have written here. Here what we have seen is that no matter what alpha is, it may be any permutation. If gamma is a T cycle, then alpha, gamma, alpha inverse is also a T cycle. So these cycles that you see here, gamma 1, gamma 2, we are considering in place of these cycles things which look like this, which we will later see are conjugates of these gammas. Okay, this type of formation is called a conjugate of the element that we have in the middle. So these conjugates, by what we are stating here, they are also cycles. The first one has length n1, the second one has length n2, and so on. So that's it, we have got what we wanted. Now by what we concluded above, alpha gamma I alpha inverse is a cycle of length ni. Hence, alpha beta alpha inverse is again also just like beta the product of k cycles of lengths these. This part may look a little bit confusing now by what we concluded above, a little bit vague about what we are exactly saying. This is the conclusion. By that conclusion we are having this. Although it can be understood, but if you want to be more specific, what you can do is that you can keep this conclusion in one paragraph and then start a new paragraph, so that you can mention here, now by what we concluded in the previous paragraph we have this. If you want, you can do write the solution like that, but anyway it's now over for us. Next, (52) let alpha and beta belong to Sn. Prove that beta alpha beta inverse and alpha. Okay. Prove that beta alpha beta inverse and alpha are both even or both odd. Okay. So they are simultaneously even or simultaneously odd. It cannot be that one of them is even and the other is odd. Are what is it, both even or both odd? Oh, so here the author is writing beta alpha beta inverse, although it has nothing to do with the previous exercise, but there we had alpha beta alpha inverse. I don't know whether it's a conscious effort or not, but it looks like Gallian is want to throw us off here. If we are too invested in the previous solution and we are it took us a long time to find the solution, you are repeating this thing in your mind, alpha beta alpha inverse, alpha beta alpha inverse. Suddenly this may cause confusion. Whether it's consciously because of that he has written beta alpha beta inverse or not, that I don't know. I don't think this is a conscious choice, but just a simple observation. And the thing is that if you are just simply thinking of alpha beta alpha inverse religiously in your mind, you may suddenly consider beta alpha beta inverse, whereas in your mind you are thinking of this, and then make the mistake of considering beta here. That is, there is a danger. But anyway, let's see the solution. Okay, so what we are claiming here is that alpha and beta are again any permutations, and beta alpha beta inverse and alpha are both even or both odd. Fine. Let alpha be equal to alpha 1, alpha 2, alpha k, where these are two cycles. We know that every permutation is a product of two cycles in possibly several different ways. So that means this representation is not unique, and in fact the number k is also not fixed. However, something about this k is fixed, namely its parity. If k is even, then in any such representation that k stays even, and if it is not, then it is not. And in fact that's how we classify permutations into these two classes, either it's even or odd. So we mentioned that we know that in such a representation of alpha, the parity of k stays fixed. That means if it is even, then it's even. If it is odd, then in all such representations it is odd. That number is odd, although the actual numerical value of the number may change. Say for example, if it is 2, then in another representation it may be 4 or 8 or 100, but it will never be equal to say 33, because that is odd, right? So by the previous exercise, and now we are going to use the previous one, the 51st one. By the previous exercise, okay, so how are we going to use the previous one? You see here alpha is a product of k cycles. Each one this time has length 2, that means n1, n2, n3 all the way up to nk, all of them are equal to 2 in this case. So by the previous exercise, beta alpha beta inverse will also be a product of that many cycles of that same length. Beta alpha beta inverse is a product of k2 cycles. So that means because in both the permutations, alpha as well as beta alpha beta inverse, when you are expressing them as products of two cycles, that k has appeared in both of them. So that means either both of them are even when k is even, or both of them are odd when k is odd. Hence so that's just the solution. Next, what is the smallest positive integer n such that Sn, the symmetric group of degree n, has an element whose order is greater than 2n. Has an element of order greater than 2n. And the answer actually is given at the end of the text itself, where you have the answers. So let me just write that down, and because simply the answer is mentioned and nothing else is mentioned, since it's a number, it's going to be a number. So that's not the entire solution, of course. So let me just write and then I will say what it means. In S9 we have the element, actually there are many such elements, but this is one of them. This 4 cycle times this 5 cycle, whose order, you can clearly see what its order will be. It will be the LCM of the cycle lengths, that is the LCM of 4 and 5, which is 20, and 20 is greater than 2 times 9, which is 18. But why 9? It turns out that 9 is the smallest such value of n, and that's where you have to do some extra work to show that it's the smallest. As this, we have the element this, whose order is, let's just show how we are getting the order also. This equal to 20, and which is greater than 2 times 9. A small thing about writing this dot, okay, I'm not sure whether I mentioned this before anywhere in my videos. You see, when you write a decimal point, you write that here in the bottom, but when you write use dot as a symbol for the multiplication operation, you write it in the middle, okay, 2.9. It's called C dot in LaTeX because it's a central dot as opposed to L dot, which is a lower dot. Okay, so this is greater, so this does not mean 2.9, okay, it means 2 times 9, which is equal to 18. So there is nothing else to see in this case, because in this group you have in fact found one element whose order exceeds 2n. But now here I leave some work to you. Show that for n less than 9, Sn does not have any element whose order is greater than 2n. You have to only deal with only some finite number of cases, and it's not very big. You just have to look at 8 cases, and they are also rather, each one of them is rather small. Now if you are worrying about, okay, small means, what do you mean by small? For example, S8 is not a joke. It has 8 factorial elements, which is an extremely large number, of course. But you see, to calculate the order of an element, you don't actually have to find all the elements. That is because we have already seen, because we find orders like taking LCMs of cycle lengths now. So you just have to look at the possible cycle structures, so that you can write an element as a product of disjoint cycles. So you just have to see that. For example, in S8 you will have elements that look like this, each one of which is a product of a 3 cycle and a 5 cycle. The actual symbols may be anything, disjoint, of course, that thing is there. So you may have, for example, 1, 2, 3 here, and then 4, 5, 6, 7, 8, or you may have 1, 2, 3, 4, 5, then 6, 7, 8 here. But all such elements will have a single order, and that order is the LCM of 3 and 5. So at least in this case, this specific case, you see that 2 times 8 is 16. So this is not exceeding 16, but it got very close. It is 15. You will see that no matter what n you take, and for that n, no matter what cycle structure you consider, you will see that all possible orders will be less than or equal to 2 times that n. So that's how you will show that no lower value of n, that is lower than n equal to 9, gives you that kind of element where the order exceeds 2n. So that part I leave to you, because it's a routine calculation. And we move on. One of the great things about mathematics is its precision, its definiteness. All the definitions have definite meaning, objective meanings, which mathematicians unanimously agree on, and all the results have a certain, what can I say, certain permanence about them. It's not like you have found a proof of some result which is mathematically sound, and it has been checked over and over again, and it has been found to be sound, it's logically correct. Then no matter what happens, that cannot be changed, and that is not the case with scientific areas, or subjects coming from actual hardcore science, where if you find a statement, there is of course no way of logically proving something in science. Everything comes from experiment, so things are subject to whatever happens in the future. If something changes, then you have to either modify that statement or completely abandon it. So it's transient, it does not stay the same. However, in mathematics it stays the same, and there is also this aspect of precision. Everything is precise. But the moment you start applying mathematics outside of mathematics itself, the precision of course goes. Nature is so complex. So any theory that you may come up with, which of course has some mathematics inside of it, some differential equations or something, all such theories are only an approximation. Each such theory is only an approximation to the actual reality that it is trying to describe. Okay, everything. So the laws that you see in, for example, physics, Newton's laws or Einstein's laws, in quantum mechanics you have quantum mechanical laws, all of them actually are approximations, and they are called laws because they have matched with experimental results so many times that they have gained this status of apparent permanence. But see, Newton's laws have been so successful for so long, and yet we have Einstein's general theory of relativity, for example, in gravitation. So that thing is not there in mathematics. Once something is proved, it's proved forever. Let's solve another one. Let n be an even positive integer. So n itself is even. Prove that the alternating group of degree n, an, has an element of order greater than n if and only if. So it's an equivalent statement. N is greater than or equal to 8. So what we are saying here is that n is, note one more thing, that n is not any positive integer. Okay, we should not forget that n is given to be even. Now under that condition, this alternating group an will have at least one element whose order is greater than n if and only if n is at least 8. So that means this thing does not happen for lower even values of n, namely n equal to 2, 4 and 6. Okay, so we have to prove that. And also when n is greater than or equal to 8, in all such, for all such values of n, we do have elements in an whose orders exceed n. Okay, and we have to also keep in mind that we are not dealing with the entire symmetric group but only the alternating group. The only element So we start from the bottom, we take the smallest possible value of n equal to 2. The only element in A2 is the identity element, or simply is the identity whose order is 1 and 1 is less than 2. So it, of course, it's not greater than 2, it's not even equal to 2. Okay, then we look at A4. In A4, the elements are of the form identity, then of course we have this kind of product where we have to keep in mind, because we are dealing with even permutations, so we have to have an even number of 2 cycles that we will be multiplying, and this turns out to be, what will it be? Let us quickly calculate. And here we are not going to say anything more about these symbols, only that A, B and C are different symbols. Okay, if they look different, they are different. So A goes to C and then C is unchanged by this, so AC, then C goes to A and then this one sends A to B, then this one does not affect B, this one sends B to back to A, so that means this is a 3 cycle. And a product of 2 disjoint 2 cycles, and that's it. We don't have any other type of things, because there are only 4 symbols available. The respective orders are identity, of course, have order 1. This is a 3 cycle, so it has order 3, and this is LCM of 2 and 2, which is 2. So we are not exceeding 4, we are not even reaching 4 also. And then we have 6. For n equal to 6, of course, there are some possibilities. In A6, the elements are of the form, it's better to merge these 2 sentences, like this. We write till this and then semicolon, the respective orders are this. In A6, the elements are of the form E, again like before, AB, AC, which will be equal to ACB, then ABCD, but there are others also. For example, there will be a 5 cycle a cycle of odd length actually is even, but let's also write why it is even. We express it as a product of 4 2 cycles, and that's why it's even. AE, AD, AC, AB. So 1 1 1 1 1, like that we partition 6. 2 plus 2 plus 1 plus 1. Those 1 plus 1 do not, they correspond to 1 cycles. Then, oh, this is not a disjoint cycle, so actually this means 3 plus 1 plus 1 plus 1, that is corresponding to this. Then here we have 2 plus 2 plus 1 plus 1. Here we have 5 plus 1. So what else can be there? Oh yes, the product of a 2 cycle and a 4 cycle. And both of which are even, so this is also even. There is no need to show this as a product of an even number of 2 cycles. And that's just about it. I mean, there are other possibilities, but they will give you odd permutations, not things in A6, but in general in S6, outside of A6, and the respective orders are the respective orders are 1 for E, then 3 for this 3 cycle, then 2 for this product of disjoint 2 cycles, then 5, and finally LCM of 2 and 4, which is 4. Let's just show that also. That is equal to 4, and all of them are less than 6. None of them is exceeding 6 or even being equal to 6. Now then we come to those values of n where we are claiming in the statement of this exercise that we will in fact have elements whose orders exceed n. And we look at these two cases. First, for n equal to 8 and 10, an has the element, I mean in each case has this element. This 5 cycle multiplied with this 3 cycle. You see, when n is 8, then of course you have 8 symbols. When n is 10, you have 2 additional symbols, but you just don't use them. So in both A8 and A10, you will have this element whose order is the LCM of 5 and 3. This is equal to 15, and 15 of course is greater than 10. So automatically that is greater than 8 also. Okay. Next, for n greater than or equal to 12, an has the element. In this case, this is the element 1, 2. And it will go till, let me write one more symbol, 6, n minus 1. Okay, what is the length of this symbol? I mean the length of this cycle. The length is n minus 1 minus 5 plus 1 to include the 5 also. That means n minus 5. Now this is where evenness of n comes into play. Because n is even, n minus 5 is odd, that means this cycle is a cycle of odd length. So it's an even permutation. Just like here, you have a cycle of length 5. So you have been able to write it as a product of 4 2 cycles. Here you again, just like that, you can write this permutation as a product of n minus 6 2 cycles, and n minus 6 is even, so this is an even permutation. with two extra 2 cycles, so that also is even, and that's how we know that this belongs to AN. We need to mention this because we have already sort of stated that it is AN has this element, so we mentioned within brackets. Note that since N is even, this is not my solution. I did not sit down and thought of this solution. I saw it somewhere, but I think it's a pretty standard solution. It's not that someone really went through, of course someone went through the effort and found this solution, but it's not an extremely difficult one. Okay, and I'm sure that it's not that just that place where I found this one, it will be found elsewhere also. Note that since N, so I just simply wanted to mention that this is not my solution. Note that since N is even, this cycle belongs to AN, and that's why this entire thing also belongs to AN. The order of the above element is what? LCM of the cycle lengths. Now because you see n minus 5 we have just now seen, n minus 5 is odd, so LCM of 2 and n minus 5 is 2 times n minus 5, that is 2n minus 10. And what is 2n minus 10? Because our n is greater than or equal to 12, so this is greater than or equal to 24 minus 10, that is 14, and that is strictly greater than, oh, so what, no, that's not what I wrote here. What the hell am I writing? That's not what I wanted to say. This is equal to n plus n minus 10, and because our n is at least 12, so this thing is greater than or equal to n plus 12 minus 10, which is equal to n plus 2, and that thing is strictly greater than n. Yeah, this is what I wanted to conclude, that there is an element in AN whose order is strictly greater than n. So here the solution ends, and here let me end this video also. The subsequent exercises, of course, we will solve in the next Gallian update, which is about group theory. And tomorrow we again have analysis, where we are I think we completed the section on series of non-negative real numbers. So tomorrow we are going to see rearrangements of series. What happens when we rearrange the terms of a series, whether convergence is affected or not. So we are going to see those things. So see you tomorrow with real analysis. If you want to say something about these things, you can write in the comment section below, or you can mail me at my usual address. The link will be there in the description. So see you tomorrow with real analysis. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.